Fabulous. Good morning. I'm glad to be able to join you finally. So I'm Alice Shelfick from the School of Engineering at the University of Edinburgh. I'm going to share with you this morning some of the complementary capabilities that we have within the school, and particularly within the Institute of Bioengineering, of which I'm the head. Obviously within the university we have the medical school and access to clinical resources there. I'm not going to cover that. That's not really my domain. The MDMC does have a clinical lead, Fiona Dennison, who I'm sure is far better at sharing their abilities with you. So I'm going to review kind of domain areas, competence areas, and just look at a few examples of the sorts of manufacturing techniques that we have within those. So the first of those I'm going to talk about is tissue engineering, and particularly the fabrication of the scaffolds. So in tissue engineering, you grow cells on a scaffold, and then they become a piece of replacement tissue. To manufacture the scaffolds, we use an array of different techniques. So electrospinning is one of the commonly used ones, and we can do that to create randomly oriented fibers, directionally oriented fibers, or something in between. And those we can create in all the usual array of polymer molecules that you would use in scaffold formation. So polylactic acid, polyglycolic acid, and so forth. We can also, in hybrid electrospinning, we can integrate polymers to help the biology recognize the scaffold as a substrate that it's happy to sit on. And so that's integrating protein molecules into the electrospinning process and functionalizing our scaffold. We also use high internal phase emulsion systems and directional freezing to create open pored structures and porogen leaching as well. So the sorts of things we can do with that are shown on the left there. So that's a scaffold for cartilage, showing directional oriented material deposited on top of an open cell structure. More recently, we've also moved into bioprinting. So this is where you can, in essence, 3D print those scaffold structures. So we can 3D print directly, but the inks that we use can also include cells. So those are called bioinks. So we can directly print 3D structures which integrate cells within them. So that's a sort of recent competence that we've added to our tool set. We also have colleagues, Pankaj in particular, so good they named him twice, who's looking at bone mechanics. So he looks at finite element modeling, so taking medical imaging, so CT, micro CT, and X-ray, and using those to create more representative finite element models of structures, both at the micro scale and also the macro scale. So on the left there, it's a pelvis annotated with all those mustard-colored fibers. Those are the muscle insertions and ligament insertions that act on the pelvis. So you can look at the mechanics of the bone structure. He's also started to integrate consideration of viscoelastic effects within his finite element modeling. To complement that, we also have a full set of mechanical characterization equipment. So the usual suspects, so tensile testing, we can also do fatigue testing, nano indentation, and we have a rheometer as well. Nothing unusual about those, but the particular important thing there is we can also use them to look at biological structures and very soft materials. So we have load cells for our tensile tester that will be able to characterize very weak materials. So we have some colleagues who are also looking at nanotechnologies, in particular Michael Chen, whose domain is in surface nanoengineering. So decorating surfaces, functionalizing surfaces to provide some sort of useful output. And often that's in sensing. So on the panel there, you can see a device where he has decorated a glass slide with a graphene nanosheet with LDH nanoparticles integrated into it to create a biosensor for ions. So in the example there, copper ions and silver ions. So you shine on a light and you get a different photoluminescence coming out. The change in photoluminescence is correlated to concentration of the ion there. So you can do that on flat surfaces, you can do that on nanoparticles, those can be integrated in diagnostic devices. He also works in creating nano needles on the surface. So there's normal to the surface needles growing up, which can be used in a whole range of different applications. For example, transfection of cells. Catherine Dunn and myself are working on DNA nanotechnology. So this is using DNA as a structural molecule. So instead of having it encoding the genetics, we use its ability to zip together to be able to create structures. So we can zip DNA into physical shapes, compose them together, and self-assemble quite complicated devices. So these are two examples from the literature, unfortunately not ours. The top one there is a 3D device. The bottom one is the world's smallest representation of a Mona Lisa, just a half micron across. It's made up of tiles of DNA origami. So this is DNA that's zipped itself together into a small tile, and then you can assemble tiles together to make a little picture there. So a 4x4 array of these small DNA tiles. So very capable in terms of creating nanoscale 3D structures and then decorating those structures with useful things. So great in biosensing, potentially in electronics, and creating new electromagnetic materials and so forth. So really powerful building technology. We also consider biofluid handling technologies. So Simona Di Martino is particularly interested in chromatography and chromatography columns. So how you can extract valuable molecules from a sample. So 3D printing those columns, but also looking at how fluid flows through 3D structures. So computational modeling, 3D printing of the physical artifact, and looking at novel geometries, novel materials, functionalization of materials, and so forth. We also have in the Scottish Microelectronics Centre the ability to create digital microfluidics, as it's now called, or electrowetting and dielectric, as it used to be called. So this is a sort of chessboard technology where you can move fluid droplets around, you can merge them, split them, dispense them, and so on. So that's a competence that the Scottish Microelectronics Centre has, along with a number of others. So they are also working on implantable devices, not dissimilar to the Sonopel, but these are some microchips that are intended to be implanted alongside a disease to be able to monitor the disease through treatment. So this is work of Alan Murray and Stuart Smith. Stuart's also working on dielectrophoresis. So the left-hand panel there is showing a dielectrophoresis device where you can sort cells. On the right there is a microfluidics device, so very good for cell characterization and sorting. We can also grow cells on top of electrodes to look at their bioimpedance. So that allows us to look at cell proliferation and motility and viability and so on. And finally, we can also make implantable devices that will release drug on command. So that's, again, work of Stuart Smith. So the Scottish Microelectronics Centre has a lot of competence that it can share. Other useful capabilities, not so much in the manufacturing space, but I thought I'd highlight as well. In the Institute of Digital Communications, it has deep expertise in biomedical signal processing, including the application of artificial intelligence and machine learning for biomedical applications. So looking at EEG, for example, the work of Javier Escudero. And then also the bioimaging SRF, so small research facility. So it's a facility where you can book time on unusual imaging modalities, so label-free imaging. So the little video that you see bottom right is a video taken through a window inserted in the gut of a mouse. So what you're looking at there is blood flow within a tumor that's growing in the belly of a mouse. So we've been studying angiogenesis in tumors using this technology in collaboration with the Edinburgh Cancer Research Centre at the Western General Hospital. I think I have rattled through enough there. Obviously, if you want to know anything more about the complementary capabilities that the University of Edinburgh can offer, I'm more than happy to answer any of your questions, either in the Q&A session or feel free to contact me. I'm Good Global. Thank you.
Alistair.